Good day everyone, my name is Jedi Picasso from DCPET 31 and today I'll walk you through 5 insightful topics covering some of the latest advancement in tech and the intricate process behind chip manufacturing and microprocessors. We'll start by exploring Infineon's approach to microchip manufacturing, diving into how silicon and precision engineering come together to form these essential components. Next, we'll discuss TechAltar's take on the challenges in chip production, shedding light on why this process is so complex. We'll then break down pho- photolithography, as explained by Jaewang Lee, and how it transfers intricate circuit designs onto silicon wafers. Following that, we'll look at DIY with Ben's guide on CPU creation, detailing the intricate steps from sand to CPU. Then finally, we'll shift gears to Simply Learn's top tech skills for 2024, highlighting the hottest fields driving innovation. And so join me as we dive into these topics. Now, imagine the tiny chips that power your smartphone or computer. It's amazing to realize that these chips actually start as sand, mostly made up of silicon dioxide. But because pure silicon isn't available in nature, it has to be purified. This then involves heating it at a very high temperature to separate the silicon from the oxygen, forming a pure single crystal cylinder called a boule. At this stage, the silicon is so pure that there's only one unwanted atom for every 10 million silicon atoms, a level of precision needed to make modern technology work. Once we have the pure silicon, the next step is to make it conduct electricity. Pure silicon on its own doesn't conduct well, but adding small amounts of other materials like phosphorus or boron changes that. This process is called doping. It allows certain areas in the silicon to conduct electricity, which is necessary to create transistors. Transistors are then like tiny switches that control electrical signals, and each one can be turned on or off to represent the ones and zeros of digital code. This small step allows us to build all sorts of complex electronics. From there, the silicon wafer goes into a clean room, a space almost entirely free of dust. Here, very tiny patterns are printed onto the silicon using light and UV exposure, layer by layer, to create the complex circuits inside each chip. Each step is then in this process is incredibly precise because even a single speck of dust can ruin a whole batch of chips. This process highlights just how careful we need to be to make the devices we use every day. Finally, after many steps and tests, each wafer is sliced into individual chips which are then packaged to be ready for use in our devices. High-power chips like those used in electric cars are designed with special features to handle high currents. So from sand to circuit, each transistors in a chip represent a level of skill and precision that's easy to overlook but truly amazing. Now, moving forward onto why chips making are so hard. Imagine this, back in the 1960s, adding just a few transistors to computer chips was a huge step forward. Then, an engineer named Gordon Moore noticed a trend. Every couple of years, we were doubling the number of transistors we could fit on a chip. This prediction, known as Moore's Law, became the tech industry's goal. It fueled decades of innovation, and companies invested millions to make it a reality. But making chips today isn't easy. It's one of the most complex tasks in modern manufacturing, as each chip requires thousands of tiny parts, each doing something different, and they're built in specialized steps. In fact, most companies only focus on one small part of the process. For example, companies like Intel design the chip's language, called an instruction set, which helps the chip communicate. But once the design is ready, it's usually sent off to a separate company, called a fab, to be built. The most famous fab today is TSMC, based in Taiwan. TSMC uses machines that can cost over $100 million each and are capable of creating patterns so small that a speck of dust could ruin an entire chip. One machine they use, called an EUV ultraviolet lithography machine, uses lasers to etch incredibly fine lines on silicon. It's amazing that we're able to do this because just one misstep can make an entire batch of chips unusable. This separation of design and manufacturing has led to huge advances in technology, but it's also created challenge. TSMC and a few other companies control much of the global chip supply. This concentration of power has caught the attention of countries like the US, Europe, and China, and they're all racing to develop their own chip production abilities, especially China, which uses more chips than it makes. In the end, the story of chip making is one of both teamwork and extreme precision. So it's amazing to think that every piece of tech that we use depends on these chips, crafted with such care. We don't often think about it, but the technology we use every day is powered by some of the smallest and most precisely made structures in the world. Now, discussing photolithography. Now imagine you're holding a tiny chip that powers your phone or computers. How did we get all those tiny intricate patterns onto such a small surface? This is where photolithography comes in, a process that uses light to print these patterns onto silicon wafers. The word photolithography comes from Greek roots, photo for light, then litho for stones, and graphene for writing. It's like writing light on stone, but in this case, the stone is silicon. Alphonse Poitevin developed that technique in 1855, and though it's evolved, the essence of photolithography is still about using light to transfer shapes onto a surface. Here's a quick breakdown of the steps. So first, they take a silicon wafer, which is prepared with chemicals to remove any impurities. Then a thin layer of silicon dioxide is applied as a mask film. And then a special material called photoresist is spread all over the wafer in a thin, even layer using a process called spin coating. Then once coated, the wafer is exposed to UV light through a mask that has the design pattern we want. This light changes the chemical structure of the exposed photoresist areas. The developer is used to remove the altered parts, revealing specific shapes on the wafer. Then, these shapes are further etched into the silicon, and we repeat this layering process to create multiple levels, forming complex chip patterns. Now, the level of detail or resolution in photolithography depends on two things: the numerical aperture of the optical system and the light's wavelength. Shorter wavelength means finer patterns. The industry once relied on mercury vapor lamps, but now uses lasers with even shorter wavelengths to achieve higher precision. As the chips get smaller, we're packing more transistors into each one, aligning with Moore's law, which predicts a doubling of transistor density roughly every 2 years. Today's technology allows us to work at a scale as small as 14 nanometers, about 10,000 times smaller than the width of a human hair. Companies like ASML have advanced the technology, providing equipment capable of creating the chips that power our digital world. Now discussing onto how a CPU is made. Creating a CPU, or the central processing unit, is a fascinating journey that starts with designing circuit diagram. Experts worldwide collaborate to design complex integrated circuits like microprocessors, graphic processors, and wireless communication chips. The process begins with the manufacturing silicon wafers from quartz sand. To create these wafers, a large crystal is pulled from purified silicon melt, resulting in a perfect silicon lattice ready for transistors. However, keeping these crystals free from impurities is crucial, like dust or dirt, so they are admitted and handled in specially designed dust-free clean rooms. Each silicon disc then arrives in a hermetically sealed container, packed with 25 wafers, and begins a journey through hundreds of manufacturing steps. One of the key techniques is photolithography, where circuit designs are transferred to the wafers using light akin to a slide projector. First, the silicon disc is coated with a photosensitive material. UV light is then shown through a mask onto the wafer, altering the exposed areas of the photoresist, which can then be washed away using a developer. This creates a template, and the unprotected parts of the wafer are etched away, forming billions of tiny current switches, transistors on each wafer. Next, the wafers undergo ion implantation to set the electrical properties of the transistors. Silicon being a semiconductor has a variable conductivity, which is adjusted by introducing dopant atoms into the silicon structure. These dopant atoms find their place in the silicon lattice at a high temperature, allowing for a precise control over the material's conductivity. Given the intricate nature of this manufacturing, a clean room as large as 2 soccer fields is needed. Processes are carefully monitored with automated systems operating within sealed production lines to maintain a pristine environment. In the following steps, copper wires connect billions of transistors, forming the integrated circuits. However, before this can happen, the wafers must be thoroughly cleaned to eliminate any lurking particles. A barrier layer is applied to prevent short circuits, and trenches are filled with copper, which is then ground down to insulate each connection from the others. Global Foundries became the first company to adopt copper for large-scale production, paving the way for advanced multi-core processors used today. Electron microscopes monitor every manufacturing steps, inspecting the atomic structures on individual transistors to ensure quality. In about 2 months then, the wafer is transformed into a massive integrated circuit containing conductors that span multiple kilometers and connect around 100 billion transistors, all in a space no longer than a fingernail. The final step is in producing microprocessors, or the CPU, involves packaging the chips. Tiny thin silver pellets are applied to the wafers to link the chips to their frames. The flip chip method is used to bond each chip securely, which is then sealed with a protective cover. Lastly, we are going to discuss the top 10 technologies to learn in 2024 as by Simplilearn. So, with over 2.4 million job openings in tech as of 2023, it's an exciting time to consider a career in this field. First up is the blockchain. It's not just about cryptocurrencies, as it's a secure way to record transactions across various industries like finance and supply chains. Next, we have augmented reality and virtual reality, or AR/VR scenes. These technologies are transforming gaming, education, and healthcare. Companies like Meta and Google are hiring, and professionals can expect about $95,000 annually. Now coming in at number 3 is the Internet of Things, or the IoT. This connects everyday objects to the internet, making our lives easier. At 4, we have 5G technology, which is set to change the game for internet speed and connectivity. Then the machine learning, a key part of the AI. It helps machine learn from data, powering everything from recommendation systems to fraud detections. Then the 6th one is the cybersecurity. With rising cyber threats, professionals who can protect data are in high demand. Firms like Cisco are hiring with average salaries of $130,000. Then 7th is edge computing, which processes data closer to its source for faster response. Companies like AWS are seeking experts. 8 is biotechnology. This field is changing healthcare with innovations like gene editing, and experts can expect around $80,000. 9 is quantum computing. This technology can solve complex problems beyond the reach of traditional computers. Then lastly, The top technology to learn is artificial intelligence, as it's revolutionizing industries and offers salaries up to $160,000. And all companies all over the world are obviously actively looking for AI professionals. So, in summary, these technologies are shaping the future, and learning them can open the doors to amazing career opportunity. So, now, after watching these 5 videos on chip manufacturing and technology, here are some of my takeaways and learnings throughout the video. First, I learned about the intricate process of chip manufacturing from Infineon, as it's incredible to see how microchips are made, starting from silicon wafers or sand and going through various processes like doping and etching. Next, Tech Altar video highlighted the challenges in making chips. Factors like the complexity of designs, the need for ultra-clean environment, and the high cost of machinery make chip production a daunting task. This emphasizes why semiconductors are so valuable in today's tech-driven world. Next, Jaewang Lee's video on photolithography broke down the step-by-step process used in chip production. This method is crucial for creating the intricate patterns on chips. So understanding this technique helped me appreciate the technology's advances that allows us to fit billions of transistors onto a single chip. Then, watching Ben from DIY with Ben explain how a CPU is made brought the whole processes to life. Seeing the components come together and learning about their functions gave me a deeper understanding of what make our devices so powerful. Finally, in Simply Learn video on the top technologies to learn in 2024, I was very excited to see the focus on areas like AI, IoT, and cybersecurity. So with over 2.4 million job openings in tech, it's clear to see that these skills are in high demand. And it's an excellent time to start learning. So in summary, these videos not only educated me on the fascinating world of chips manufacturing, but also inspired me to explore emerging technologies. That's all. My name is Jedi Picasso from DCPET 31. Thank you for watching the video.